All right, let's dive into one of the weirdest and coolest rules in the entire quantum world. We're going to use a particle you've known your whole life as our guide, the proton. And we're going to ask a question that sounds super simple, but the answer? Well, the answer changes everything. Why can't you just break one?
First things first, we've got to get our heads around some seriously strange math. Because down at the subatomic level, 1 plus 1 doesn't always equal 2. Nope. Sometimes when you slam two particles together, all that energy just merges into one single event. This little paradox, it's the key to solving our proton puzzle.
I mean, think about it. You drop a vase, it shatters, right? You get a ton of smaller pieces of a vase. It's just common sense. But if you try to do the exact same thing to a proton, what you get seems to defy logic itself. So what on earth is hiding behind that question mark?
To figure that out, we have to know what's holding the proton together to begin with. And that brings us to this incredible concept, this unbreakable bond called quark confinement.
See, here's the first surprise. A proton isn't some tiny, solid marble. If you could zoom in far enough, you'd see it's actually made of 3 even smaller particles. They're called quarks. So, if it's made of 3 parts, why can't we just snap it into thirds?
The reason is quark confinement. It's a fundamental rule of the universe that basically says quarks are glued together by this thing called the strong nuclear force. And that glue is so powerful that you can never, ever find a quark all by itself.
Okay, the best way to picture this is to imagine a cosmic rubber band. It's tying those 3 quarks together. But here's the truly bizarre part. Unlike a normal rubber band that gets weaker when you pull it, this one gets stronger the farther you stretch it. Way, way stronger.
So let's play this out. You've got your 3 quarks, just hanging out. You decide to grab one and pull. That strong force rubber band starts to stretch, and as it does, it starts storing a crazy amount of energy in the space between the quarks. You keep pulling, and the energy builds and builds until finally, snap!
So what happens when that cosmic rubber band breaks? This is where things get really wild. All that energy from the snap has to go somewhere, and it brings one of the most famous equations in history into the game. And there it is, E equals mc squared. Energy equals mass times the speed of light squared. Albert Einstein's masterpiece. This simple little equation is the absolute key that unlocks the whole mystery of the unbreakable proton.
And here is the mind-bending twist. All that energy you just pumped into stretching the strong force, it doesn't just vanish in a puff of heat or light. In the quantum world, that pure energy instantly, and I mean instantly, transforms into new mass. It literally creates new particles out of absolutely nothing. So this is what you're left with. You don't get a free quark. No way. The universe says, I'll see your attempt to break a particle and I'll raise you one. The original quarks snap back together to remake the proton, and all that energy you used creates a brand new particle, something called a meson. You tried to subtract, but the universe decided to add.
Now, I know this sounds like some wild, abstract theory, right? But this is something physicists see happen every single day. And they do it at the biggest machine humanity has ever built.
Yep, we're talking about CERN's Large Hadron Collider. This is the place where scientists take protons, get them going at 99.99% of the speed of light, and just smash them together. It is the most violent, high-energy way you could possibly imagine to try and break a proton. The official name for this is deep inelastic scattering, which is really just a fancy way of saying they're using the insane energy of one proton like a battering ram to get a peek at what's going on deep inside another one.
Now, your gut tells you this should be like a car crash, right? Proton bits flying everywhere. But that is not what happens. Instead, for a split second, the 2 protons and all their energy merge into one single, unified, super high-energy event. That's our 1 plus 1 equals 1 idea right there in action.
And the energy packed into that single event is so huge that it can literally create things that weren't there before. The famous Higgs boson, that's how we found it. It was forged from the raw energy of a proton collision. 2 protons went in, and a whole shower of new, exotic particles came out.
Okay, so let's tie this all together. Let's recap the fundamental rules of this quantum game that make it completely impossible to ever truly break a proton. It all boils down to one single solitary number that the universe refuses to break, and that number is 1.
This number has a name. It's called the baryon number. See, a proton is a type of particle called a baryon, and it gets a value of +1. And the standard model of particle physics has a very strict, non-negotiable law. You cannot have fractions of this number. There is no such thing as half a baryon, which means, fundamentally, there's no such thing as half a proton.
So let's just look at how different these two worlds are. Traditional logic says dividing a proton by 3 should give you 3 quarks. But quantum reality says, nope, impossible. You just make more particles. We think adding energy breaks things, but the quantum world says adding energy creates things. A collision isn't just two things breaking, it's two things becoming one new system.
And the final result of all these bizarre rules? A particle that is almost unbelievably stable. I mean, the theoretical half-life of a proton is so long, it's many, many, many times the current age of the entire universe. Protons are, quite literally, built to last forever. So, in the end, you can't break a proton because the fundamental laws of mass, energy, and conservation just won't let you. It's an incredible reminder that the universe does not care one bit about our common sense. And it really makes you wonder, doesn't it? What other basic rules about our reality are just sitting there, waiting for us to realize we've had them wrong all along?